Is the universe hiding more than what meets our eyes? What if I told you 85% of the universe's mass is invisible and we call it dark matter? Yes, you heard that right, dark matter. It's a cosmic enigma that has been teasing and tantalizing the minds of astrophysicists and cosmologists for decades. Dark matter is not just your ordinary matter. It's not made up of atoms or molecules or anything we can see or touch. It's a unique kind of substance that doesn't interact with light, hence its name, dark matter. But it's out there lurking in the cosmic shadows, influencing the universe in ways we're still trying to understand. Dark matter has a significant role in the grand scheme of the universe. It's the invisible glue that holds galaxies together. Without it, galaxies would simply drift apart, and the cosmic web, the large-scale structure of the universe, wouldn't exist. It's the gravitational scaffolding on which the visible universe is built. But even though dark matter plays such a vital role, it presents a formidable challenge to our understanding of the cosmos. It's like a cosmic jigsaw puzzle with most of the pieces missing. We know it's there, we see its gravitational effects, but we don't know what it's made of. This mysterious substance has become one of the most pressing problems in modern physics, a problem that has sparked a fervent quest to unravel its nature. Experiments are underway, telescopes are pointed towards the skies, calculations are being scribbled on blackboards, and theories are being formulated and tested. The hunt for dark matter is a scientific saga, a journey that takes us to the very edge of our understanding of the universe. It's a story of exploration and discovery, of the known and the unknown, of the seen and the unseen. So how did we stumble upon this invisible entity? Let's delve into the annals of astrophysics. Our cosmic detective story begins in the 1930s with Swiss astronomer Fritz Zwicky and his perplexing galaxy clusters. Zwicky, a man ahead of his time, noticed something peculiar. The galaxies in these clusters were moving too fast for the amount of visible matter to hold them together. The gravitational glue was missing. Zwicky proposed an audacious idea. He argued that there must be an unseen form of matter, a dark matter, keeping these galaxies from flying apart. But at the time, this idea was met with skepticism. It was too revolutionary, too outlandish. After all, how can something exist if we can't see it? The answer lies in the subtle influence of gravity. Gravity is the great cosmic puppeteer, silently orchestrating the dance of galaxies. It doesn't care if you're visible or invisible, it pulls all matter alike. This is how dark matter reveals itself, not through light, but through gravity. As decades passed, more evidence piled up. Astronomers observed gravitational lensing, where the path of light from distant galaxies is bent by the gravity of intervening matter. They noticed that the light was bending more than it should given the amount of visible matter. Once again, the unseen puppeteer was at play, hinting at the presence of dark matter. Another piece of the puzzle came from the afterglow of the Big Bang, known as the cosmic microwave background radiation. The slight temperature variations in this radiation across the sky provide a snapshot of the universe in its infancy. And guess what? The patterns in this baby picture suggest a universe composed largely of dark matter, so we have galaxies moving too fast, light bending too much, and temperature variations in the early universe. All these observations point towards the same conclusion, an unseen gravitational puppeteer pulling the strings of the cosmos. This puppeteer, dark matter, doesn't interact with light but shapes the universe through gravity. These observations set the stage for a new form of matter, one that doesn't interact with light but shapes the universe through gravity. The universe, it seems, operates on a different set of rules which include unseen matter and mysterious energy. Our quest to decipher these rules has led us to the Lambda Cold Dark Matter Model, or Lambda-CDM Model. This is the prevailing blueprint for understanding the cosmic structure, the grand design of the universe. The Lambda-CDM model makes some bold propositions. It suggests that the universe is chock full of cold, non-relativistic particles. These are the dark matter particles. Cold here refers to the fact that these particles move much slower than the speed of light. This slow movement gives rise to structures in the universe, like galaxies and galaxy clusters. But there's more to the Lambda-CDM model than just cold, dark matter. The lambda in the name represents a cosmological constant, a mysterious energy that permeates the universe. We know it as dark energy. Dark energy, though elusive, plays a crucial role in our understanding of the universe. It's this dark energy that causes the universe to expand at an accelerating pace. So the Lambda-CDM model paints a picture of a universe filled with slow-moving dark matter particles and permeated by dark energy. It provides a theoretical framework that aligns remarkably well with our observations of the cosmos, from the large-scale structure of the universe to the cosmic microwave background radiation. This model, while widely accepted, still doesn't tell us what dark matter is. For that, we turn to particle physics. In the world of particle physics, two hypothetical particles stand out as potential dark matter candidates: WIMPs and Axions. Let's talk about WIMPs first, short for weakly interacting massive particles. As their name suggests, these are envisioned as heavyweights of the subatomic world. Despite their size, they're elusive primarily because they interact weakly with ordinary matter. This means they can pass through matter without leaving a trace, a characteristic that makes them incredibly hard to detect. But if we can, it would validate their existence and their role as the main constituents of dark matter. Experiments are underway in underground laboratories around the world, shielded from cosmic rays and designed to detect the rare instances when a WIMP might collide with an atomic nucleus. It's a bit like trying to hear a whisper in a hurricane, but the potential payoff is monumental. Now, let's navigate to the other end of the mass spectrum to meet Axions. These particles are ultralight, so light that they're almost ghost-like. Initially proposed to resolve an issue in the theory of quantum chromodynamics, they've since been co-opted into the dark matter story. If Axions exist, they could form a vast, coherent field known as a Bose-Einstein condensate, effectively acting like a wave on cosmic scales. The Axion Dark Matter Experiment, or ADMEX, is an ongoing effort to detect these elusive particles. The experiment uses a strong magnetic field and a sensitive microwave receiver in the hopes of coaxing Axions into revealing themselves. Both WIMPs and Axions offer compelling possibilities, and the hunt for them epitomizes the pioneering spirit of astrophysics. It's a thrilling journey into the unknown, where every potential discovery could rewrite our understanding of the universe. But what if dark matter isn't made of WIMPs or Axions? What if it interacts with itself in ways we haven't thought of? As we delve deeper into the universe's secrets, some theories suggest dark matter might have a life of its own. This brings us to the concept of self-interacting dark matter, or SIDM. It's a fascinating proposition that dark matter particles may not be the solitary wanderers we think they are. Instead, they could interact with each other through non-gravitational forces, a characteristic that stands in stark contrast to the behavior predicted by the traditional cold dark matter models. This hypothesis arose in an attempt to reconcile discrepancies between the properties of galaxy clusters and substructures observed in reality versus those predicted by simulations. On the other hand, we have modified Newtonian dynamics, or MOND. This theory takes a different route altogether, proposing modifications to the laws of gravity at low accelerations. Instead of invoking the existence of dark matter, MOND attempts to explain the observed galactic rotation curves and other astrophysical phenomena by tweaking Newton's laws. However, while intriguing, MOND faces its own set of challenges, notably in constructing a comprehensive theory that successfully explains a wide range of astrophysical observations. So, with SIDM and MOND, we see two alternate paths in the quest to understand dark matter, each with its own set of implications and challenges. While these theories are intriguing, the jury is still out on what dark matter actually is. As we stand on the cusp of cosmic discovery, the hunt for dark matter is far from over. We find ourselves in an era of unprecedented scientific endeavor where cutting-edge technology and innovative theories coalesce in our quest to understand the universe's unseen components. From high-energy particle accelerators probing the smallest scales of existence to powerful telescopes peering into the furthest reaches of the cosmos, our tools for exploration are constantly advancing. Experiments are underway in the deepest mines and the coldest laboratories, attempting to detect elusive particles like WIMPs and Axions. These endeavors are complemented by theoretical work as physicists attempt to reconcile dark matter with the standard model of particle physics. The future of this cosmic quest is filled with promising prospects, the potential for paradigm-shattering discoveries, and the certainty of new questions. So, we continue our cosmic detective story, exploring the universe's hidden corners, ever hopeful that one day the mysteries of dark matter will unfold.